Good morning, Year 13. My apologies for not being able to join you, but that's how life is at the moment. A quick recap of what we covered before half term, before I dive into the content for today. We have been looking at sequences and series, chapter 3 in the Pure Book. And we looked at arithmetic sequences, GCSE linear sequences, and arithmetic series when you're adding all those terms together, and then geometric sequences, which is the growth and decay stuff you saw at GCSE, and then the sum of a geometric series. And we saw that these were very similar to the GCSE content. There was nothing major new here, just a kind of reworking of this for thinking of it in an A-level way, getting formulas in terms of the first term and the difference or the ratio. But those formulas were in the formula book, so life was nice and simple. They often involved setting up and solving simultaneous equations, so they were a bit fiddly in times, but nothing completely drastic in there. What we're going to look at today is the next step, which is the sum to infinity of a geometric series. So something particular happens when you continue a geometric series indefinitely, and it doesn't always work. So we'll have a quick look at an example that does and one that doesn't, and then we'll kind of tidy up our ideas and formalize everything a little bit. So the two series I'm going to look at real quick are doubling and halving. So the doubling sequence is 2, 4, 8, 16. So the doubling series is going to be 2, and then 2 add 4 is 6, and then 6 add 8 is 14, and then add the 16 is going to be 30, and so on. And what you can see is that actually this series is just slightly more than doubling every time, because every new term is double the previous one. And so our total is growing very, very quickly. In fact, the further on we go, the faster the total grows. And this sequence is known as divergent. And divergent just means that it moves away from a fixed point. So this thing is growing faster and faster as we move forwards. But in contrast, the halving sequence, well, we start with 1, but then the series adds on a half. So we get 1 and a half. And then it adds on a quarter, which is going to be 1 and 3/4. And then from there we add on an eighth, so that's going to be 1 and 7/8. And then we add on a 16th, so it's going to be 1 and 15/16. Every new term is half of this little gap we've got away from 2. So what happens as we move forward is what we're adding on is smaller and smaller every time, and what we're going to do is we're going to get nearer and nearer to this fixed value 2. So this is called a convergent series because it converges on, it narrows in on a fixed point. In this case, it's convergent on 2. And I think we can kind of see intuitively that it's going to aim for 2 just because of how the sequence is built up. It's not always obvious what our converging value will be from the start, but in this case I think it's fairly clear. And so we've got these two different things going on. And the key question is, first of all, when will it be divergent and when will it be convergent? And the answer to that actually is very, very simple. And we can get the answer from looking at the formula. So our formula has a whole bunch of numbers in, but these numbers are mostly fixed. So A is our first term and it's fixed. 1 is just the number 1. This one is fixed. This R is our common ratio and this is fixed. In fact, the only thing that's changing each time is this little part, this term, r to the power n. So it's the r to the power n which really has the impact on what the total of our series is at every point. And hopefully you will remember that if the base is between 1 and -1, then as the power gets bigger, the value of this term gets smaller and smaller. If our base is between 0 and 1 or -1, then that term decreases as the power gets larger. And in fact, we tend to write this using modulus notation. So we say as long as the size of r is less than 1, this sequence will converge. It will be convergent because this term will gradually get smaller instead of bigger. In particular, what's happening is as n heads towards being infinitely large, r to the power of n is heading towards being 0, because as the power gets bigger, the value gets nearer and nearer to 0. And we can be more specific than that. That means s infinity, the sum to infinity, is a times 1 minus, well, as n heads to infinity, r to the n heads towards 0 over 1 minus r. And we can tidy this up a little bit because that 0 is not important. So this turns out to be just a over 1 minus r. Now, it'd be really nice if we could confirm that this works with the example we had with intuitive answer. So in our example, a, the first term, was 1, and r, the common ratio, was a half. And that means that s infinity, the sum to infinity, is 1 divided by 1 minus a half. And 1 minus a half is a half. 1 divided by half is 2, which is our intuitive answer, and it's exactly what we expected. So, really quick summary. The sum to infinity is a over 1 minus r, as long as r is small, less than 1. And helpfully, in the geometric series part of the formula book, we have the formula for the sum to the first n terms, and we also have the sum to infinity, and it reminds you in there that r has to be small. So this is information in the formula book for you as a gentle reminder. And that's the key idea. In the next video clip, I'm going to go through a couple of simple example questions so you know what to do with this, and therefore you can get on with some practice.